And we'll go from current slide. And Tef is here. Okay. Anyone else come in since the call draw? All right, finally, the whole system's up. Let me first make a couple of announcements. They're hopefully fairly minor, but they may have some impact. Normally on Fridays, I'm on the Birmingham campus, 7:45 to 11:45, and all those are supposed to be office hours, except they love calling meetings during on Fridays. But as far as I know, I don't have any meetings tomorrow. But I won't be on Birmingham campus. I've got an infusion tomorrow. I'll be at the Perkin Clinic, probably 7-ish or so, and the infusion is supposed to start sometime after 8, and it usually goes close to 8 hours. So I will not be on campus at all tomorrow. So if you're looking for me, and can I get your name, please? Jayla. Huh? Jayla. Jayla, got it. Now finding is the other part. Yeah, I got it. Okay, finally. Thank you. Yes. All right. So I will not be on Birmingham campus or either campus at all tomorrow. Then next week, Monday should be about normal. I think I've told you this before, but the math team, when we meet, and it's been very infrequent, but when we do, it's usually during my office hours, 3:15 to 4:45. The one student has to go to class, and we usually don't stay that long anyway. But then after we finish with math team, office hours, which could be as little as 3:45 to 5:15. 4:45 to 5:15. So it's not a lot of time, but not always do we meet. Like last time, she couldn't. In fact, this week she couldn't either time. And let me get your name, please. Second. Johnson. Okay, I missed it again. Okay. My hearing is so bad, I haven't made it out yet. Josh, got it. Okay. Okay. But office hours on Monday, if math team meets, it'll be something around 4:45 until 5:15. If we don't meet, 3:15 to 5:15. And I probably have to leave right at 5:15 on Monday. Most of the time I can stay later if I want to, but I've got a meeting that I'm supposed to be at Monday. All right. Tuesday, my only office hours are from 12:15 to 1:15, which is also my lunch hour. But I'm in the office then most Tuesdays and Thursdays. However, my afternoon class is going on field trip, so I have to, as soon as I get out of the 12:15 class, I have to rush to the Birmingham campus, pick up the van, and rush back here before 1:15. So I will not be in my office at all 12:15 to 1:15 on Tuesday. I'll be on the road getting the van and bringing it back. By the way, we'll talk about it today. Okay, so after that, hopefully the office hours will be a little more regular, whatever that is. Okay, any questions on anything we've covered so far? Okay. Well, we're finishing up chapter 1, functions in the graphs, and today we're approaching inverse functions. Now, what are inverse functions? What do you think of, or do you think of anything when you hear that word, inverse functions? Well, guess what, team? You've been doing them your whole mathematical life. What's the first operation you learned? Well, maybe second. Okay, early in kindergarten, first grade, so we're at elementary. What's the first mathematical operation you learned? Second? You learned subtraction before you did addition? That's the same. Yeah, okay, well, counting was the first. Okay. And then after counting was addition. Okay, and once you finally got that down, all those addition cards and everything else, Then they popped on you subtraction. But what did subtraction do? Undo addition. It's the inverse operation. And then you thought, wow, I finally got math under control. And then they laid on you multiplication. And boy, all those times tables and things like this. But finally, you sort of got those down. And about the time you felt comfortable there, division undoes multiplication. Inverse operation of multiplication. Okay? Later, sometime or another, you got to raising numbers to powers, right? Exponentiation. Okay? And then what was the inverse function of that? Well, yeah, okay, you're doing exponentiation. Square roots, exactly. If you square a function, then take the square root, you undo it, inverse operation. Okay? We've been doing that our whole mathematical lives, and we're going to continue to do it. Now we're going to do it with functions. So, we'll first, and I really don't care for the book's approach to this, we'll first find inverse functions informally and verify the two functions are inverse functions of each other. Okay? We'll use graphs of functions to determine whether a function has an inverse function. Not all functions do. We'll use a horizontal line test to determine whether functions are one-to-one. Where did that come into play? That's how we know if they got an inverse function. And then, finally, we'll do it algebraically, which is far better than informally or any of the other ways. To me, we should have started there almost, but not quite. But let's do it. Inverse functions. All right. Several ways to express a function, remember? You can do it as a written thing, like spell it out. You can write y is equal to a function of x. You can write a mapping, or you can do a set of ordered pairs. Remember, that's one of the first ones we did, right? We know you can do the set of ordered pairs to represent a function. So what if we have this function, f of x equal x plus 4. Now, normally we say, what's the domain of that? All real numbers. So let's say for now, we're only going to use as our input a. The domain is just going to be 1, 2, 3, 4. Okay? What happens if we plug in a 1 through that? 5. Plug in a 2, 6. Plug in a 3, 7. Plug in a 4, 8. Okay? So, there's the output set. That's the range. So, with that in mind, with this limited domain, and therefore a limited range, we can write this function either as its descriptor, or we can write it as a set of ordered pairs, 1, 5, 2, 6, 3, 7, 4, 8. Okay. In this case, by interchanging the first and second coordinates of each of those ordered pairs, you can form an inverse function. Okay? And that inverse function is called F inverse. Can I get your name, please? Sandria. Okay, got it. Oops. There you are. All right. I actually already marked you here. I was psychic, so I knew you were coming. Okay. So, that is the inverse function, denoted by F inverse. Now, the book is going to say this later, but let me say it now. Okay? Have to have some way to express it. If we had a variable like x, and you put x to the minus 1, what does that mean? Say again? In what sense? Yes. The multiplicative inverse. Let me get my pen set up, if I can find it. There it is. Okay. Why is there we go, finally. This thing is awfully slow. There we go. All right. So if you have x, slow, okay, there we go, to the minus 1, that means 1 over x. Now that is a type of inverse. That's a multiplicative inverse, okay? And if you had 7 to the minus 1, that's 1 over 7. Anytime you have a number or a variable raised to the minus 1, that means a multiplicative inverse, 1 over. That's not what this means. If you have function to the minus 1, that means the whole inverse function, not just the multiplicative inverse, the entire function is inverse. Okay, you see there's no multiplication involved with this if you flip those two orders. Okay, so your inverse function is a function also, and now it maps from set B to A. So what was the output, the range of the first function, is now the domain of your inverse function. And what was the input, or the domain of the first function, is now the output, or the range, of the inverse function. Okay? So the inverse function, now this one just happens to be, the first one was x plus 4. The inverse function, if you think about it, yeah, it makes sense for that to be x minus 4. Because whatever you put into it, subtract 4 from it. 5, 1, 6, 2, 7, 3, 8, 4. And if you'll go back and look, that's exactly reverse the order of your ordered pairs. Okay? Note that the domain of F is the range of F inverse and vice versa. The domain of F inverse is the range of F. Okay? Also note that F and F inverse have the effect of undoing each other. Just like subtraction undoes addition, division undoes multiplication, square roots undo squares, inverse function undoes the other. If you start with the domain of F, some value in there, an X, you operate it with the F, we'll use that same function we did before, and you get the range of F, which is different from this one. And that's your F of X, or Y. But if you start with this and operate with the inverse function, you come back to exactly the same value you started with. Okay? Given a 1 here, 1 plus 4 is 5. Given a 5 here, 5 minus 4 is 1. You come back to exactly where you began. They undo one another. Okay? Any questions? In other words, when you form the composition of F with F inverse, guess what you should get? Here we go back to composing functions. You should wind up with the identity function because you start out with what it is. So let's start. Do F operating on F inverse. We're doing the composition. Remember we did this at the end of the last section. Okay? And what do you do first? Plug in what F inverse is. What was it? On the last slide. X minus 4. Now you take your F and operate on X minus 4. Well, your F was X plus 4. So you take what's here, X minus 4, add 4 to it, and sure enough, you wind up with X, which is what you started with here. If you compose one with the other, you wind up with the identity function. Now, the good news is, what if you started with F inverse, operate with that on F? When you do what's innermost first, what was F function? X plus 4. And if you operate on that with the F inverse, and the F inverse was X minus 4, so you take this thing, X plus 4, and then subtract 4 from it, and lo and behold, you wind up with X again. Now, if you remember, I said most of the time, composing two functions is not commutative. F of G is usually not the same as G of F. But remember I said, except for a few special cases. This is one of those special cases. If you're operating with one on the inverse of itself, then F of F inverse is the same as F inverse of F. And not only they're the same, but they always wind up being the identity function. Always. If they're inverses of each other, they will. So there's a test, so we can tell whether we have an inverse or not. All right, now, here we have our first example. Find the inverse of f of x equals 4x. Okay? Does anyone want to make a guess about what the f inverse might be? Say again? Say again? X over 4. Okay? This will multiply the input by 4. This one's going to divide the input by 4. That should undo it. Okay? Let's see if it works. If that is your f inverse, what is F of F inverse. Okay, remember how you did the composition? Where do we start? Innermost. So it'd be F of, what'd you say? X over 4. Okay. And F function started with 4 and multiplied by what's in the parentheses. And what's that? X over 4. And when you multiply those together, what do you get? Ding, ding, ding. Good. That's what you expect to get. But to truly verify, we need to do it the other way. So let's start with F inverse and take that of F. Okay, I say start with it, but where do you start here? The innermost function. Plug that in first. What's your innermost function? 4x, right? F of x. So that's F inverse of 4x. You just do it plugging in. Now we do what F inverse we said was x over 4, so you take whatever's in the parentheses, and that happens to be 4x, and divide it by 4, and sure enough, again you get x. Same answer, identity function for both of them. Yes, those are inverses of each other. Make sense? Now these are very simple ones and really easy to do just by looking at it. Okay? Don't try this on more complicated functions. You'll probably drive yourself crazy because there's so many different ways you can put them together. Okay? But let's see what they did. Any questions before I erase it? None? Okay. All right, let's see what they do. First, the function f multiplies each input by 4. To undo that, let's divide the input by 4, which would be f inverse. This would be our guess. F inverse is x over 4. That's just a guess until we verify it. How to verify it? Do your composition of the two. F of f inverse is f operating on what we guessed was the inverse function, x over 4. And the f function takes whatever's in the parentheses. It takes 4 and multiplies it by what's ever in the parentheses, x over 4, and that certainly gives us x. Halfway there. Have to verify the other way as well. F of f inverse, f inverse of f, well, f of x is 4x. F inverse takes whatever's in the parentheses and divides it by 4. You take 4x, divide it by 4, ding, 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 we've got x again. So f of f inverse must equal f inverse of f, but not only that, they both must equal the identity function x. Does that make sense? All right. So here's our definition of an inverse function, as if we haven't been doing it already. If f and g are two functions such that f of g of x happens to be x and x alone, that's for every x in the domain of g. That's where you're starting. And at the same time, g of f of x is equal to x for every x in the domain of f. Okay? Then, under those conditions, if both of these are true, both of them being identity functions, then under these conditions, the function g is said to be the inverse function of f. The function g is denoted by f inverse. That's read f inverse. Don't even say f to the minus 1, because then you might think that means 1 over. Read it as f inverse. So f of f inverse has to be x, and f inverse of f has to be x. If it's not, they're not inverses of each other. The domain of f must be equal to the range of f inverse. The range of f must be equal to the domain of f inverse. Now, the first one we did, domains and ranges were all real numbers. That's not always the case, okay? So you have to make sure that this is, it looks like it's the same, but you see, this x is the stuff that's in the domain of g. This x is the stuff that's in the domain of F. And if those happen not to be the same, they may not be the same values, but they always come out being just the identity function X. Okay? Now, this is what I was saying before. Do not be confused with the use of -1 as a superscript, okay, to denote the inverse of F inverse, okay? In this text, whenever you see a function raised to a -1, that doesn't mean it's a power. That means it's an inverse function. So don't confuse that with a power. If it's after a variable or after a number, yes, it's a power. But after a function, it is an inverse. Okay? Sorry we use the same notation, but it's just gotten into the lexicon and not going to leave. Okay, that's not the reciprocal of F. That is not an exponent in the sense of raising it to a power. If the function g is the inverse of F, then it must also be true that F is the inverse of g. So if one is the inverse of the other must be the inverse of the one. Okay? For that reason, you can say that the functions f and g are inverses of each other. That's another way to express it. Okay? Inverses of each other. Okay. Now, they're skipping example 2. So let's go back and do example 2. Which of the functions, and by the way, after every example I think in the text, there's always a checkpoint, okay? And if you have the checkpoint, I would suggest that whenever you get out of class and have some free time, first opportunity, go back and do the checkpoints. Because right now, you're spectating, okay? You're watching me do the problem. Now, I'm trying to get you involved with it, but most of you are spectators, okay? In order to master it, you got to be participants. You got to be the players, okay? So get to it and start doing the checkpoints. Okay, so let's do example 2. Which of the functions is the inverse of f of x is equal to 5 over x minus 2? Okay, we have two possibilities. We have g of x, which is x minus 2 over 5. And we also have h of x, which is 5 over x plus 2. Okay? Now, I don't know if any of you can tell just by looking, but how you really tell is by plugging in and doing the verification. What is that verification? Okay? Now, what f of g of x. That's how you verify if it's an inverse or not. Do the composition. And what would you do first here? Just write down the f, and instead of g of x, write down what g of x is. What is it? X minus 2 over 5. Now we take f and operate f on that input. Okay? Well, what f says is to start with the number 5 and put it over this thing in the parentheses, which is 5 over x minus 2, and then subtract 2 from that. Get out of there. Okay? Okay. Doesn't look too promising, does it? What I would suggest doing next is this is what some books call a complex fraction, where you have a fraction within a fraction. Then take the least common denominator of all those fractions. That's the only one you got is x minus 2. Multiply the numerator and denominator by that. So this would be x minus 2 times over x minus 2. Okay, so this will give you, I'm going to come up here and do it, 5 times x minus 2 over, and when you multiply x minus 2 by that, you just get 5 minus 2 times x minus 2. Still doesn't look very promising. Let's try it. be 5x minus 10 over 5 minus 2x plus 4, and that would be a mess. 5x minus 10 over 9 minus 2x. Is there any way in the world that's going to come up being x? Yes. Is what? X minus 2 over 5, not x over. Okay. Not 5 over x. No. Oh, you're right. You're right. This right here should be. You got it. Thank you. Okay, I was looking at the wrong one. Okay, you're absolutely right. Very good. Good catch. That's x minus 2 over 5. Ha! Okay, that makes things a little bit, in fact, quite a bit easier. Let's get rid of this and that and basically all of this, okay? And start that one over. All right, good. Now, our least common denominator is 5, so multiply the numerator by 5 and the denominator by 5. Okay, so that gives you a 25 in the numerator, and when you multiply 5 times this, you get x minus 2, and then you get minus 2 times 5. Okay, so that'll be 25 over x minus 2 minus 10, that's 25 over x minus 12. Anyway, we're going to get an x out of that? No. That is not. And I sort of don't like doing something wrong, and that's what we did. We should have known that wasn't going to work. So let's forget about g. That is not the inverse function of f. Well, let's see about the other one. H. Could that be the inverse function of f? I'll get rid of all this just because I may need the room to write otherwise. Okay? That's what you do. Now, what do you do to test to see if h may be the inverse? F of h of x. Okay? And what do you plug first? 5, yeah, h. 5 over x plus 2. Okay? Now we operate on that with the F function. Well, here's the F function. And F function starts with 5, divides by what's in parentheses. And that's 5 over x plus 2, right? Minus 2. Hey, we can just remove those parentheses because they're not really doing anything for us. There's nothing in front of it. And what's 2 minus 2? 0. So those add to 0. And then you got 5 over x. Well, what's that? That's 5 divided by 5 over x, which is the same as 5 times. How do you multiply, divide fractions? Oh, you got to remember that, huh? Invert and multiply. X over 5. Well, the 5's cancel out. What do you get? Ding, 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 ding. And x. That's promising. Has that proven that these are inverses of each other? No, it's required for them to be, but you got to do one more. What's that? Yeah, you got to do the other way. And what's that? H of f of x. Okay, and what do you plug in first here? Yeah, 5 over x minus 2 is your f. Okay, and you plug that into the h function. What's the h function? It starts with a 5, divides by what's in the parentheses, right? And that's 5 over x minus 2, and then you add 2 to that. Do you see that? The h function starts with 5, then divides by whatever's in the parentheses here. Okay? It's 5 over x minus 2, and then adds 2 to that. All right, let's do that first part first. Sort of like we did before. 5 over that is the same as 5 divided by 5 over x minus 2. And how do we do that fraction? 5 remember how to divide fractions? Times x minus 2 over 5, right? Multiply by the reciprocals. Ha! So that 5's go out. They've been dating, okay? So that gives you x minus 2 plus 2, which gives you x. Yes, the inverses, both ways, you produce, if you do the composition both ways, you get x. Yes, that's the inverse. Now, I'm not sure I would have ever looked at this and said that's going to be the inverse of it. Probably not. If you think about it, though, it kind of is. You got a subtraction here. You do have an addition here. You have a division here. And you still have a division. So it doesn't quite look like you turned it into a multiplication, but it does work. So you see, you can't always look by inspection. If you had tried to do this by guesswork, I think it would have taken you all day to come up with that one. By the time you finished doing all those, you probably would have missed it anyway, even if you hit it right, because it would have been driving you crazy keeping all those things in line. So there's got to be a better way than inspection. But right now, all we're doing is verifying, okay? So let's now look. Any questions before I erase this? Okay. All right. Now let's look at the graphs of inverse functions. Now I wish we had done something first. They're doing it kind of backwards in my mind. We're going to get there. The graphs of a function f and its inverse, f inverse, are related to each other. They're second cousins twice removed, okay? In the following way. If the point AB is in the graph of f, right? Remember, ordered pair AB, what must be an inverse, f inverse? BA, okay? Then the point BA must lie on the graph of f inverse, and vice versa, okay? What that means is that graph of f inverse is a reflection. Now they just pull this out of the air of some unknown body part and say this is it. Is a reflection across the line y is equal to x, which is what turns out being your identity function. And sure enough, if A, B is on it, BA, those are the same. A, and B, yeah, that's the same on both of these. If you come over here for x, go up there for y, go up here for x, up there for y, those are on it. B, A, B, okay? Yeah, they reflect across the y is equal to x. Now, what they haven't told you, and I'm going to tell you now, they're going to get to it later, notice this f of x is strictly increasing. That almost goes to 0 there, but doesn't. It's never constant. It's strictly increasing. But look at f inverse. It's almost constant down here, but not. And it's always increasing too. So, both f and f inverse have to be either strictly increasing or strictly decreasing. Okay? We're going to get to this later, but that's an issue. Since they have the graph here, I wanted to point it out to you. Okay? In other words, f can't back up on itself. Neither can f inverse. Okay? So let's do example 3. Sketch the graphs of the inverse functions. They're telling you these are inverse functions. I don't know if you believe them or not, but let's try it. Okay? Okay. How do we graph f? Say again?
Plugging all real numbers straight.
You could. What's an easier way?
Start at -3.
Say again? What kind of function is that?
It's
A linear function. It graphs into a straight line. And what form is it in?
start at -3.
Oh, yeah, on the y-axis. That's the y-intercept. 0, -3, which is plugging in also. And then what else? Up 2 for 1 over. So go up 2 for 1 over, up 2 for 1 to the right. My spacing is not very good. Up 2 for 1 to the right, up 2, 1 to the right, or down 2, 1 to the left, and it's something like that. There is your F function. You want to do F inverse in a different color, just so it'll be easy to tell?
Green.
Green, light or dark?
Dark.
Dark, okay. Dark green. Okay, here we go. Now, before I do this, I want to slightly change it here, if you don't mind. This is I want to distribute the 1/2. 1/2 x plus 1/2 of 3, which is 3/2, which, by the way, is 1.5, right? So its y-intercept is 1.5. It's going to be right there. Kind of a boo-hiss, right? Now, what it's doing is up 1/2 for every 1 it goes over. So up 1/2 for every 1 it goes over. And after that, I'm going to go up 1 for every 2. 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 Something like this. Down 1/2 for 1 over, and then down 1 for every 2 to the left, down 1 for every 2 to the left. Okay, something like this. So here, yuck, this is not very pretty. Okay, there's the graph. Yuck, that's not right. Wait, why did you let me do that? You're not paying attention, are you? Okay, I'm not. Okay, let's start this over. 1.5 is positive, not negative. Duh. That's up here is where it starts. Right? Yeah, you should have stopped me right there. Up 1/2 for 1 to the left. Down 1/2 for every 1 to the right. I said it backwards. You got it. Slope of positive 1/2. Then after here, up 1 for every 2 to the left. Up 1 for every 2 to the left. Up 1 for every 2 to the left, something like that, and something like that. Down 1 for every 2 to the left. Oh, my spacing's terrible here. But anyway, what you get is a straight line with a slope of 1/2. Yuck! My straight lines are not very straight. Okay? Forgive me, I can't draw. Okay? Now, here's the thing to note. I'm going to choose this color. Red. All right. Let's do the identity function here. It's got sound effects even. And down like this. And guess what? If I had drawn them properly, they would be reflections across the identity function. Y is equal to x. Okay? Make sense? And it says do that. And show that the graphs are reflections of each other across the line of y is equal to x. I didn't get my lines very well. My major problem was my spacing was terrible. Okay, but other than that, it worked out all right. Okay. Any questions? Let's see if they can draw a little bit better than me. I doubt it, but let's see. Okay. Any questions before I erase? Okay, first thing to do, well, they didn't show much of anything, did they? Here is the first function, f of x equal 2x minus 3, y-intercept of minus 3 up to right 1. And the other is, they didn't do it, they just drew it in here. Sure enough, they're right. It starts at 3/2, which is 1.5, and then goes up 1/2 for every 1 to the right, down 1/2 for every 1 to the left. And then after that, up 1 for every 2 over, go like this. There's your second function, f inverse, and sure enough, they cross at the common point 3, 3. Okay, so 3 and 3. But look at the other points. -1, -5 is on F. Plug it, if you had done it like Danielle was suggesting, that we plug in numbers. If we plug in a -1 here, -1 times 2 is -2, -3 is -5, so -1, -5 is on this one. But if you had plugged in a -5 in this one, -5 plus 3 is -2, half of that is -1, -5, -1's on this one. See, you just flip the order of the coordinates. This is 0, -3, this is -3, 0. This is 1, -1, this is -1, 1. This is 2, 1, this is 1, 2, 3, 3, 3, 3. That's the same, and you keep on going. So sure, those are inverses of each other, reflecting across the identity function y is equal to x. Any questions on that? They said test a few points. They all work. Okay, the ones that we've done so far. Any questions? That was example 3. We can also do this. Note the following list. If you had done a t-table to begin with, or however you want to call that, x, y, these are your x's, those are your y's, or f of x is y. You could have done this. That's what Danielle was suggesting. You could have done the same thing with this one and gone this way. Okay? Now, these you can choose any x you want to, and it works well. On these, since you're taking a half of it, you'd love to have this thing in here to be an even number. Well, for that to be an even number, you need that to be odd, because the sum of two odds is even. Sum of the even and odd. So you pick odd numbers here for x, and that's what they did. And sure enough, they show they reflect each other. They are inverses of each other. Does that make sense? So if we had followed Danielle's advice, we'd have seen this from the very beginning. Right? All right. So that's example 3. Now they're skipping example 4. So let's do example 4. Whoa. Gotta get my color back. Okay. All right. Example 4. Verifying inverse functions graphically. Verify graphically that the functions f of x is equal to x squared. And this is only good for x greater than or equal to 0. Why? X squared is good everywhere. Okay, but we'll see in a minute. And g of x, let's do that in a different color. You want green again? All right, with green. G of x equal square root of x. Now, in my gut, I feel like those must be inverses of each other. Okay, but what do we notice about g? What does x have to be here? It's inside a radical. It's got to be greater than or equal to 0. Okay? Okay, now that really has little to do with this one. Okay? They look the same, but this is for different reasons. Okay? And we'll get that in a second. Okay? That one, because it has to be. You can't take the square root of a negative number. This one doesn't have to be, because you can square a negative number, no problem there. But we'll see later why that's the case. Okay. So let's do what they told us. Okay? Let's do a graph of both of those. Now, since x's are always positive on both of those, I don't need to put my y-axis way over there. I can move it way over here. Okay? Now, before I start graphing, I want to point this out. What's the value of your range here? All positive. What's the value of the range here? All positive. Okay. Now, the fact that this is all positive, that means this has to be. And you can sort of see what's happening now. So I can draw this line down here, here. So we're all in the first quadrant. How does f of x equal x squared. Look, give me a few points. Wait, let me tick off a few. I won't need that many by far. Okay, I can go on up if I need to. Give me a few points. A little louder. 0, 0. Someone said 2, 4, I think. I just dawned on me what you said. 2, 4. What's another one? 1, 1. Okay, I'm going to need a few more points. 3, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Just barely got that one in. That's as far as we can go on this one. Now that we recognize as what? A parabola, remember? And it keeps on climbing. Okay? Let's go to our g of x. Okay, give me a few points there. 0, 0 certainly works. 1, 1 works. 4, 2 works. 9, 3, 5, 6, 7, 8, 9, 3, somewhere, I don't know, 1, 2, 3, 4, 5, 6, 7. I got it over too far. Somewhere about there, I think. I can't do 16, 4, but it does something like this. Right? And guess what else I'll draw in? In red? The identity function. And sure enough, that reflects over it. 0, 0, 1, 1, 2, 4, 4, 2, or vice versa, 2, 4, 4, 2, 9, 3, 3, 9, and it just keeps on going. Now, remember the parabola does like this, the square root does like that. I didn't draw them very well, but that's it. So yeah, those are inverse functions of each other. Now, if you think about it a little bit, why didn't we do the whole parabola? What's that? Okay, it can't change direction. It has to be strictly increasing. That's one good answer. The other reason is, for this to be here, for this to be an inverse function, this would be like this. And it can't be. Why? It's not a function. So therefore, that's why this has to be greater than or equal to 0, because it has to be strictly increasing. If you include here, it's decreasing here and increasing there, you couldn't have it. Okay? That has to be that, because you can't take the square root of a negative number. So two different reasons, but indeed the case. Also, the fact that g of x is always positive, therefore your input here has to be positive. So you couldn't have negatives here, because g of x is never a negative value. Any, yeah? Points where? Oh, okay, right here? Yeah. Plug in an x. It has to be greater than or equal to 0. Start with 0. 0, 0 is greater than 0. Got it. 1. 1 squared is 1. Got it. 2. 2 squared is 4. Got it. 3. 3 squared is 9. Okay? And then doing the other way, 0. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. Okay? Yeah. I was being lazy. I didn't do a table like I should have, but I only did chairs. No, never mind. Any questions on that one? Example 4. Okay, again, it has a checkpoint as well. All right. What we've been talking about then, without knowing we were, is a concept called one-to-one functions. These are intimate functions. They're one-to-one. Okay. The reflective property of the graphs of inverse functions gives you a geometric test for determining whether the function has an inverse or not. That's called the horizontal line test. Remember, a function has a vertical line test. Vertical line can only cross a function, graph of a function once. But, you know, for it to be a function, it can wiggle and squiggle all it wants to the other way. But for it to have an inverse, it also must pass the horizontal line test. A function f has an inverse if and only if no horizontal line intersects the graph more than one point. So that parabola, if we had done the whole parabola, fails the horizontal line test. If we restrict the parabola to strictly increasing, passes. Or strictly decreasing, passes. This one would have reflected on the negative of the square root of x. That would have been fine. It just, no horizontal line can intersect the graph more than once. Okay? Which the other way of saying that is, and the book doesn't say it yet, I'm not even sure they ever do, the functions have to be what we call monotonic. What does the prefix mono mean? One, like a monocle is a single lens. Mr. Peanut on the planner's thing wears a monocle. Okay, that's a monocycle is a single wheeled cycle. Okay, so no horizontal line intersects the graph of f more than one value, then no y value is matched by more than one x value. That means you're strictly one-to-one. We already had that no, for any given x, it can only be one y. Now we say for any given y, there has to be only one x, one-to-one. A function f is one-to-one when each value of the dependent variable corresponds to exactly one value of the independent variable. Function f has an inverse if and only if it is one-to-one. The other way of saying that, if and only if it's monotonic, either strictly increasing or strictly decreasing. Gotta be, okay? Now, let's consider these two functions. Here's a perfectly legitimate function. F of x equals x squared. Plug in any x, you only get one y, right? Minus 2, 4. Minus 1, 1. 0, 0. Minus 1, 1. I mean, 1, 1. 2, 4. 3, 9. Okay? For any x, only one y, those are functions. Vertical line test wins. Passes. But if you try to do an inverse here, you lose it. Because if you reverse the x's and y's, put your y's here for your x's here, put your x's here for the y's there, then it's not. This is not a function, okay? It's not monotonic, okay? Because for any one x here, there's a y, here's a different y. Can't happen. For this one, minus 1 or plus 1. Can't happen, okay? So this one's not monotonic. It does not have an inverse, x squared. Unless, of course, we restrict the function to either strictly negative values, that would not be a problem, or strictly positive values. That would be a problem. Just can't do that. So that's what we do sometimes. If a function does back up on itself and fails the horizontal line test, we may choose a portion of the domain for which it is strictly increasing, one-to-one, or decreasing. Okay? The table on the right back here does not represent a function because input x equals 4 has two different outputs. Okay? So therefore f of x equals x squared is not one-to-one over the whole number system for all real numbers. Does not have an inverse function over all real numbers. If you restrict its domain to being only positive values or only negative values, then yes, it would be monotonic, one-to-one. All right, this is example 5a. Okay? And by the way, it says see LarsonPrecalculus.com for interactive version of this example. So this is something new in this text that wasn't in the old one. So if any of you have the old text, you may not have that. But Larson Precalculus will still have it, so you can go to it and see it. You just won't have that wording there. Here's the graph of f of x equals x cubed minus 1. Did they graph it right? Yeah. X cubed would be, remember, it's the cubic function, that parent function we remember we did, okay? And then we down one, vertical shift down. So now what was up here is shifted here, what was here shifted there, what was here, everything shifted down one. Yeah, that looks like it. Is that one-to-one? Yes. Of course, it's a function, passes vertical line test. It also passes the horizontal line test. The only place you might have a little suspicion is right there. It almost looks like it might not pass, but if you blew that up, you see that always is slightly increasing there. Even though it's very slow, it is increasing. So if no horizontal line intersects the graph more than 1 point, it is one-to-one. It does have an inverse function. Not going to do it now, but we will do something like that later. Okay? But you're guaranteed to have an inverse function because it's one-to-one. Does that make sense? So that's the A part. Let's see if they do the B part. How about this one? Alpha of x squared minus 1. Well, x squared was the parabola that's set up here like we were dealing with before. Down 1, yeah. Is this a one-to-one function? No, not on its entire domain. Because it is possible to find a horizontal line that crosses twice, not a one-to-one function. So it does not have an inverse function over its whole domain. However, if we only included x greater than or equal to 0, yes. Or x less than or equal to 0, yes, but not over the whole domain. Make sense? Okay. Let's see if there was an example 6. No. So, finally, let's get around to finding what these inverse functions are without guessing, without graphing. In fact, graphing doesn't really help us a lot either. Let's find them algebraically. Yes, this is pre-calculus algebra. We want to do it algebraically. Okay. For relatively simple functions, like the ones we did before, you can almost do it by inspection. Okay? For more complicated functions, however, it's best to use the following guidelines. Now, I don't necessarily number the steps the same way they do, but use the guidelines. You don't have to worry about what number it is. Okay? And they warn you this before they tell you what step 3 is. So let's interchanging the roles of x and y, that's what we got by saying inverse function reverses x's and y's, right? Very first thing we did. So here are their steps. I'll break it down a little bit differently. First, if you're given a function f and you're asked to find its inverse, first make sure it has an inverse. Now they say use the horizontal line test. Guess what that is? That means graphing it. Okay. I don't always want to waste or spend time graphing, so sometimes I'll just sort of think through it and say, does this have? Be careful with that, but and I'll show you some examples of how you can skip having to graph it. But you've got to make sure it has an inverse function first. So graph it, horizontal line test, whatever it takes. Number 2, or their number 2. In the equation for f of x, replace f of x with y. We've been talking about that from the day 1 in this course, right? What is f of x? Y. So instead of writing it f of x, write it as y. Okay? That's a pretty easy step. Now this one, actually I would break into 2 steps. First step, exchange the x and y. You wrote the y there instead of f of x, just change it. Then I would say the next step, solve for y. Why do they put them both in one step? Then, once you've done that, replace that y with f inverse. Because you swapped them, now rather than f, it's f inverse in the new equation. And then the last one, and people like to skip this one, but please do it. Verify they are inverse functions of each other. How do you do that? 2 steps there too. F of f inverse and f inverse of f. They both better equal the identity function. So to me, there's multiple steps here. Okay. So let's I'm not sure we're going to have time to do example 6. Do you think? Okay, so I think I do have time to give you some homework exercises. Yay! All right. That sounds exciting. All right. We will, let me mark my place here. Homework exercises. Do any of the odds 7 through 13. All the odds are in calccheck.com. 9 is in calcview.com. Do either 15 or 17 or both. 15 is in calcview. They're both in calccheck. Do number 19. It's in calccheck but not in calcview. Do any of the odds 21 to 31. All of those odds are in calccheck, but 23 is in calcview. Do 33. That's in calccheck but not in calcview. Do 35. It's in calccheck, not in calcview. Do either 37 or 39. They're both in calccheck. Neither one of them are in calcview. Do either 41 or 43. They're both in calccheck, but 41's in calcview. Stop there. We'll pick up the rest of those next time. Okay? Did I use most of the time left? I hate to cheat you out of a minute of your tuition dollars, so I think we used most of the time. Good deal. Have a good weekend. Of course, working on math problems and your quizzes, if you haven't finished that, will make it a good weekend, won't it? Yes. Okay.